section 611 is titled Special Right Triangles, and we're going to answer the question, is there a pattern? So question number 1 says, Darren wants to determine the side lengths of the triangle at right. Unfortunately, he left his calculator at home, and he does not remember the value of the cosine of 60. That's okay, says his teammate Jan. I see a way to figure it out. Using tracing paper, she creates the diagram at right by reflecting the triangle across side B. What is the resulting shape, and how do you know? So she takes this one, traces it, flips it over on this side, and retraces and traces another triangle. This now becomes an equilateral triangle. Okay? That's this side reflected over here, now creates 60, 60, 60. Okay? All right, part B says, what if Jan had reflected across a different side? Would the result still be an equilateral triangle? So if she reflected over this A side, would it be an equilateral triangle? The answer is no. Or if she'd reflected over the side with the 2 on it, the answer would be no. The only way to get an equilateral triangle is to reflect across that longer leg B. Okay? Part E says, use Jan's diagram to determine the length of side A. Okay? If that makes an equilateral triangle, then all 3 sides would be congruent. That means this whole side would be 2. So half of it, just the A of it, would be 1. Because then you would have a 1 and 1 combining to get the 2 of that side. And D question says, now determine the length of side B. Leave your answer in exact form. In other words, do not approximate it with a decimal. Okay? So using that Pythagorean theorem, we're going to use 1 squared plus b squared equals 2 squared, which means we're going to have the square root of 3. Okay? That's our Pythagorean theorem. All right, question number 2. Darren's triangle is an example of a half equilateral triangle, also known as a 30, 60, 90 triangle. Because of its angle measures, Darren is starting to understand Jan's methods. But he still has some questions. Help Darren by answering his questions below. Will this approach work on all right triangles? In other words, can you always form an equilateral triangle by reflecting a right triangle? Works really well on a 30, 60, 90, but will it work on other triangles? The answer is no. The triangle must have that 60-degree angle, otherwise it won't work. Okay? Has to be a 30, 60, 90, and then it's what we call special. All right, part B. What if the triangle is a different size? Show Darren how he can reflect the triangle at right to form an equilateral triangle. Then determine the side lengths of side X and Y without using a trig tool or a calculator. Simplify any radicals in your solution. Okay? Because this side is 8, if we reflected over this side, then our Y would double. Our Y would be half of whatever this side is. So you would take 8 and divide it by 2, and that would give you Y is equal to 4. Okay? Then you simply take that 4 and you multiply it by the square root of 3, and you get 4 square roots of 3. So if you don't have a calculator, most people can divide by 2 pretty easily, even if it's like a half a number. Okay? And then once you've taken half of whatever the hypotenuse to get your Y, then you're going to multiply it by the square root of 3 to get the other side. Okay? Flip over to the top of page 2. Part C says, let me straighten it out, there we go. Part C says, is the longer leg of a 30, 60, 90 triangle always going to be the length of the shorter leg multiplied by the square root of 3? Explain why or why not. You're going to say yes. One way to justify this is to show the 30, 60, 90. You can use angle similarity. That's one way. And part D, what if I only know the length of the shorter leg? You only know the length of the shorter leg. You can take that number and work backwards, which would be to multiply it by 2. So for this side M, you would take the shorter leg, multiply it by 2 to get 30. Then to get the length of side N, you would take the shorter leg and multiply it by the square root of 3. That's always going to work as long as the triangle is 30, 60, 90. All right. Darren draws the triangle right and wonders if it is a 30, 60, 90 degree triangle. What do you think? And how do you know? So if we know the hypotenuse is 7 and the shorter leg is 3, we can determine if 3 is half of 7. So if you take 7 and divide it by 2, you get 3.5. 3.5 is not 3. So this is not a 30, 60, 90 triangle. Okay? If we'd gotten 3.5, or if we'd gotten exactly 3, then yes, it would be. Okay? Now we're going to look at a 45, 45, 90 triangle. So for question 3, it says, Darren wonders if he can discover a pattern in another special triangle he knows, shown at right. Use what you know about this triangle to help Darren determine the lengths of sides A and B, and without a trig tool or calculator. Leave your answer again in exact form. Okay? If this is a 90-degree angle and at least one of the angles says 45, you know it's a 45, 45, 90 triangle. So the legs opposite the angles that are 45 and 45 should be the same. Why? Because their angle measures are the same. So if this angle and this angle are both 45, then this side and this side are going to have the same measure. So if this one's 1, this one has to be 1. So you're going to say A is equal to 1. To get the hypotenuse, you're going to multiply by the square root of 2. So 1 times the square root of 2 is the square root of 2. All right? Let's try one that's a little bit harder. We want to name this triangle. The standard name is 45, 45, 90. Most people don't even say the degrees. Like you could say 45 degrees, 45 degrees, 90 degrees, but it usually just rolls off the tongue a little easier if you say 45, 45, 90. It's also technically an isosceles triangle, and it's also a right triangle. Any triangle that's 45, 45, 90, they're all similar by angle. Part D, down at the bottom. Determine the missing side lengths in the right triangles below. Leave your answers in exact form. Both triangle 1 and triangle 2 are 45, 45, 90s. You can tell by the box, there's your 90. If one of them is 45, the other has to be 45. So the two legs are the same. So if this leg is 20, then A is also 20. To get B, you take the 20 and you multiply it by the square root of 2. For triangle 2, it has the box, which means it's 90. This one's 45, which means that one's also 45. The two legs are the same. So if this one's 5, then C has to be 5. Then you're going to take, for the hypotenuse, take the 5 and multiply it by the square root of 2. and you get 5 square roots of 2.